Hello, everybody. So I'm Johnny, and I'm going to be doing my talk today on an introduction to Netcode for entities. So, just quick introduction on myself. My name is Johnny Thompson. I'm a Unity developer. I work independently doing contracting, consulting, things of that nature. I also do content creation. So, you may have came across the Turbo Makes Games YouTube channel. If you've looked into anything about Unity Dots or ECS, you may have came across my channel. So yeah, a whole bunch of tutorials on there, some fun live streams, a lot of good stuff over there. And earlier this year, I actually released a Steam game called Dot Survivors. It's available for free over on Steam. And also over on the Unity Asset Store, I have available for purchase just a whole bunch of learning resources where you get kind of all the project files for this game, Dot Survivors, and access to a whole big website for kind of like learning about creating a full game with dots. So I'm super proud of that. But that's what this talk is not about. To talk about is an introduction to Netcode for entities. So I just want to give a little bit of an overview about what Netcode for entities is. I'm not here to say, Netcode for entities is the best and it should be used for every single multiplayer project under the sun. But I do want to talk about some of its strengths and weaknesses and to help give you an idea about what things that it kind of does well. And so if you're making a game that can kind of take advantage of some of these features, then just kind of want to give you some exposure to this and kind of maybe hope you consider it because I think it is a pretty good netcode solution. So just kind of starting things out, I want to talk about a couple of the different netcode solutions that are available through Unity. So Unity provides a couple different netcode solutions. So there's two, kind of high-level APIs. So there's netcode for game objects and netcode for entities. And they also have a low-level API where you can actually access, what's called the transport layer, where you can get, if you want to make your own kind of custom netcode solution, Unity kind of like offers you access to some of that lower level API. If you don't necessarily want to use some of the higher level stuff with netcode for game objects and netcode for entities. Of course, there are some other third-party solutions like Photon, Fishnet. You can create your own custom netcode solution, of course. Um, but just to kind of like anchor this talk, I want to do just a quick comparison between netcode for game objects and netcode for entities, just to kind of go over the two higher level APIs that Unity provides. So starting with netcode for game objects, as the name suggests, it's kind of built off of Unity's traditional game objects, and so things are kind of all managed through regular mono behaviors. So if you look at this image here, here's kind of some examples about, kind of how you would define, say, a networked object and a network transform. And you have some options about, what kind of data that you want to synchronize and everything. So this is all, again, done through regular Unity game objects and mono behaviors. Now, when we're talking about netcode for game objects, there's two different kind of like network topologies that you can use. So there's server authority and distributed authority. So server authority is where the server has the final say of what happens in a network game. There's two different ways that you can typically set up a server authority. So one of them would be a dedicated server where you have a server typically running on like a cloud machine that people connect to. And the other main option would be a client hosted option where one of the clients who are actually playing the game, they're also running the server, and you kind of do some peer-to-peer connections where all the different players are kind of connected to that one host client. So there are kind of some pros and cons with these different approaches. If you have like a dedicated server, that's going to kind of reduce the possibility of cheating because that server is kind of running on hardware that you as the developer control versus it's running on hardware that the client is controlling, and so maybe they can kind of hack into it and do some different things on there. You're typically going to get the best performance from running a dedicated server because, again, you as the developer, you can choose what hardware that your server is actually running the game on. And then there's also like no clients have to actually simulate the whole server. So, the clients are only running their client side code, servers only running the server side code. So you're kind of going to get the best performance on there. However, it can be expensive to run dedicated servers because you typically have to pay for the time that these servers are up and running. And of course, there is some latency involved. And, especially if, maybe you only have servers in one region of the world and, people from all over the world are connecting to that server. Well, depending on your geographic location to that server, there is going to be, more or less network latency. Again, another option, like I mentioned, is setting up in like a host mode where you have, the client who is also running the server. In this case, maybe the host can kind of hack into the server and kind of cheat a little bit on there. Um, but it's also going to take more simulation resources to run the host PC because, again, they have to run the client and the server on there. And the kind of remote clients, so the client who's running the server, obviously they're going to have no latency, network latency communicating with the server because it's on the same machine. However, the remote clients are going to have some latency, again, kind of depending on the geographic location from the remote people to the client running the server. Distributed authority is a little bit of an interesting thing that Netcode for Game Objects offers, where the kind of authority for different things in the world is distributed across all the different clients. So this kind of reduces the possibility of cheating because there's not like one central point of simulation. Again, it's kind of like separated across like many different clients. It also is a little bit of a performance optimization because there's not one client who has to run the full server simulation. Just everyone is running a part of that simulation. So another feature of Netcode for game objects is that it has support for interpolation and anticipation. Interpolation is just kind of a way to smooth out data between network updates. And anticipation is just kind of like a simple guess of what the values are going to be at the current network tick, kind of factoring in some latency of data being received from the server and all that. So it's not like a full client prediction with simulated rollback and everything, which we're going to be talking about a little bit later. But it still, has the ability to do just kind of like a simple guess of where things are going to be in the future, and kind of has the ability to fix some of those incorrect anticipations. So when should you use Netcode for game objects? So one reason would be if you want to use traditional game objects. When we talk about Netcode for entities, you have to use Unity ECS. So if you're still really comfortable with using Unity game objects, and maybe you already have a game built out with game objects that you want to make multiplayer, um, then that would be something that you would want to look into Netcode for game objects for. If you're not necessarily super comfortable with Unity ECS yet, yeah, maybe I would still kind of encourage you to look into a little bit because I think ECS is really cool and just like a great way to make games in general. But if you're really set on using game objects, then Netcode for game objects is going to be kind of the way that you go for that. It is typically geared more towards casual and cooperative games. These games you don't necessarily need any like really amazing full client prediction or anything like that. Or maybe cheating isn't as big of an issue in these types of casual and cooperative games. Um, and the kind of performance of these games might be a little bit easier to run, so that makes it better if you're kind of doing like a host mode type setup where the one of the clients is also simulating the server, where it's not going to be like as demanding on that system to run both the client and the server. Or if you want to use kind of that distributed authority option, then Netcode for game objects is what you're going to have to use. So now let's talk a little bit about Netcode for entities, what this talk is about. I'm just going to start with like a high level overview, and then some of these things I'm going to be going into depth on a little bit later. So if I kind of go over something quickly, just wait a sec. I have a little bit more information later in this talk. So Netcode for Entities, as the name suggests on this one, is built off of Unity's entity component system. So this synchronizes Unity ECS entities, and all the data that is being synchronized are stored in Unity ECS components. Now, Netcode for Entities is a client server architecture only, so you don't have the ability to do that kind of distributed authority thing that Netcode for Game Objects offers. But you still can run this in two different modes where you have, a dedicated server running in the cloud, or maybe a server that you kind of own and maintain, or you're doing a host mode where you're doing more peer-to-peer connections, and one of the clients is actually simulating the full server on their machine. So Netcode for Entities also does support interpolation. However, it does have a full client prediction with simulated rollback. We'll be getting into a lot more details on this later on, but this full client prediction is just a lot more accurate, and it's a better kind of prediction engine than the basic anticipation that you get with Netcode for Game Objects. Netcode for Entities can also support much higher player counts. So there actually isn't like any, hard cap on how many players can be in a game with Netcode for Entities. But I did actually see a tech demo online where somebody made a 700 concurrent users connected into a Netcode for Entities simulation, which was pretty impressive. And they were basically just saying at that point they were really just bottlenecked by the network traffic. So pretty cool that it can kind of support up to that. Again, in a very specific tech demo case. So don't expect that to happen with every type of game. So when to use Netcode for Entities? So the kind of one of the primary reasons would be because you would want to use Unity ECS and data-oriented design. Again, it's my opinion that I just really like making games with ECS and data-oriented design. I think it's just kind of like a better way to make games. So if you are interested in using ECS and data-oriented design, Netcode for Entities just fits right into using Unity ECS. It is also geared a lot more towards competitive games where you kind of want some level of fairness, where you have this simulation running on the server and you want to have this better client prediction and everything like that. That's just suited a lot more towards competitive games, maybe like fighting games, MOBAs, first person shooters, those types of things. Also, it can be used kind of if you want to make more ambitious games. Unity likes to use this verbiage for using dots and ECS to help you create more ambitious games where you're kind of pushing the boundaries of what Game Objects has to offer. So you want to create games with more players, more enemies, larger worlds. Just really when you start to get to the limits of Unity Game Objects, then that's when you want to start looking into using entities just in general. And then if you're making a multiplayer game, it makes sense to just use Netcode for Entities in that case. So I do want to briefly mention a couple of games that are made with Netcode for Entities. So one of them that I do want to call out is this Mega City Metro game. This is a publicly available demo created by Unity, and all the source code is available on GitHub. So you can actually play this game on desktop and mobile phones. You can connect over 100 players into this world at once. And it is just this kind of like large world that you can fly around and shoot the other people who are flying around. So it's fun little thing, and it really just kind of shows some of these larger, more ambitious games that you can create with Unity ECS. So this one is made from the ground up with Unity ECS, and I think it's a great example project to show what you can do with ECS, and also what you can do with Netcode for Entities. Another one that I do want to call out is Survival Kids. So Survival Kids is a game that was internally developed by Unity. It's actually published by Konami and is a Nintendo Switch 2 launch title. Interestingly enough, this game is made with regular Unity game objects, but they created a full custom setup where each of the game objects kind of has like an additional entity counterpart associated with it, and that's kind of my understanding of it is that that's what kind of does this synchronization across the netcode for entities is what they're using for the network API. So a little bit of an interesting setup, but really cool to see that the full published Unity title Survival Kids is built off of netcode for entities. All right, so let's talk a little bit about some of the getting into like some of the more specifics about things. So we'll start with entities. So entities is also kind of known as the entity component system, and the entity component system is kind of a representation of separating entities, components, and systems. It's kind of built off of these data-oriented design principles where you're kind of separating your data from your simulation logic. So, we have these structs, which are kind of data components that store the data associated with entities. And then we have separate systems to modify that entity data to make things actually happen in the game. Now, I probably could do many talks on, what the entity component system is and all the features of it. And in fact, I have done many talks on just that. And actually, at the past two JetBrains Game Dev Day conferences, I've done a talk on an introduction into data-oriented design and Unity. And then the one last year I did was called Why Dots is Unity's Silver Bullet, and just kind of went into, just kind of much more in depth about what ECS is and kind of how it interacts with this broader thing called DOTS, which is Unity's data-oriented technology stack. So if you are kind of interested, I think that would be a good place to start to kind of just get a little bit more knowledge about, kind of what you get with Unity ECS. So, kind of going with the entity component system, that separation of data and transformations, I really do think that it lends itself well to networking. This is because data is kind of easily synchronized. Because data is often stored in kind of these like simple types, which are serialized pretty easily, and we can send these across the network, pretty easily. And again, they are kind of just data. There's no kind of like methods or anything associated with them. So, we're really just synchronizing data across the network. And then we have these systems that kind of operate independently on that data. And we can kind of specify where we want these systems to run. So we can say, this system should only run on the client. This system should only run on the server. So, for example, the client is going to be handling just running, say, the input and user interface systems, where the server is kind of running, more of the game logic and kind of like, processing some of the server side networking things. Actually, typically we also want the clients to run the game logic as well to kind of predict the server behavior. But we'll be talking a little bit more about that when we get into client prediction there. So the entity component system, this kind of just enables us to have more players, more enemies, just more dynamic things. Like I mentioned, it's great for making kind of more ambitious games. We can have faster simulation times. We can also easily use the job system and burst compiler, which are great features of the Unity game engine. Now, you still can use jobs and burst with regular Unity game objects. But when you use ECS, it's extremely easy to use jobs and burst because it's just kind of, just adding in a couple extra things. Like everything that you need is already right there for you. One other thing that I do want to mention is, Unity has kind of announced this whole initiative of ECS for all, which is coming to the Unity game engine, where, basically if you have just a regular project created with Unity game objects, that each game object is going to have kind of an entity associated with it. And this is going to make it really easy for, if you were building out a game objects project and you wanted to add in some of these, cool ECS features, you can have, you can write some ECS systems that kind of, process these things for, if you have some, particularly heavy logic, those are some like, good use cases for that type of thing. And, this is a little bit of a speculation, but, it seems like that when this kind of ECS for all initiative is in place, then it's going to, make integrating netcode for entities in just a regular Unity game object project a little bit easier because there are kind of already those entities available for you. It seems like it's almost something like kind of what that Survival Kids game did, where it's built with game objects, but they kind of have some ECS entities that are kind of doing that network synchronization. So going into another topic here, just about the kind of server authoritative nature of netcode for entities. So again, this server authority is where the server has the final say of what happens in the game. This is to greatly reduce the possibility of cheating, where the client can't hack into the client code or their network traffic. Um, because the server is the thing that's actually processing all that data and saying if something can happen in the game and all that. So again, it is kind of important for competitive games where fairness is essential. Now, with this server authority, there still is going to be a delay between the client and the server. That's just kind of due to physics realities of sending data across the network. So it is going to take some time for, if you're running the game on your computer, to actually send that out to some server somewhere. That server has to take some time to process that, and then it gets sent back to you and all the other clients. So there is going to be a fair bit of delay, and unfortunately, it's not uncommon for some data to be outdated by a few hundred milliseconds by the time it actually reaches an end client. And of course, as we're talking about competitive games, this is really going to be a big issue because we want this simulation accuracy to be, as on point as possible. So let's talk about some of these solutions to latency. So one of them is interpolation. Now, interpolation is basically just a way to kind of smooth out the data received from the server. So um, it's going to kind of have some previous data and some current data, and it's just going to interpolate that data from one point to the next. This is really important for smoothing out movement in games, because often games are going to be running at a higher frame rate than the server tick rate. So, for example, with Netcode for entities, the typical default server rate is 60 ticks per second. You can increase that or decrease that as needed, but I think 60 is a pretty good one to start with. But however, let's say that the clients are running the game at 120 frames per second. So that ends up being a little bit of an issue because your game is running at double the rate that your server tick rate is. So if you're only updating the, say, positions of things on the, when it's actually received from the server, then, they're going to appear to be running at that lower, 60 frames per second in that case. Whereas, if your game's running at a higher frame rate, you want it to be much smoother. So what this does is it, just kind of smooths that out, across that full network tick. So you kind of get some of those in between values there. One of the consequences of this, though, is that the data is going to be outdated. Um, it actually ends up being a few ticks behind because there, of course, is some network latency. It takes time for that data to come from the server to the clients. And it's typically also going to be buffered by a couple network ticks because you don't always want your data to be running up to the current network tick, because if there happens to be some case where there's some little hitch in the network where there might be some packet loss, then your movement's going to be kind of jittery again of those remote clients because they're going to kind of like go up to the latest data point that they have. And they're gonna try to continue to interpolate again, but they're like, okay, well, I haven't received any new data recently, so I just kind of freeze here essentially. So it ends up getting buffered by a couple ticks, and that's just so that movement can continue to be nice and smooth, even if there is a couple ticks of packet loss. It kind of has that buffered data. So there are kind of some issues with interpolation, but it is something that you still want to use, and you do want to use it pretty frequently. Netcode for entities can take advantage of interpolation, and this is often most used for less relevant network objects. So maybe these are things that are further away, or maybe they don't have a critical impact on gameplay. We actually kind of want to have probably more things be interpolated than predicted. We'll be talking about prediction in a moment, but prediction can be quite expensive. So, if we can get away with doing some interpolation for something, it's better to do that. But again, this data can be outdated. So the kind of other solution to latency that is kind of often created for some of these networked type games is client prediction. Um, and client prediction essentially runs a local simulation of the game on each client. And what the client is going to do is it's going to guess what the server is going to do based off of the previous input data and kind of like the trajectory of that data. So it actually, the way that this works is it runs the same code on the client and the server. And that's so, the client knows kind of what the server is going to do. But the client is still kind of making guesses about what's going to happen, because anything can kind of happen in a multiplayer game. So it's really just like the client is kind of like doing its best guess as to like what this remote client was previously doing. How can we kind of like continue doing that? But ultimately the server is still going to have the final say of what happened, and we kind of need to handle some of these mispredictions as well. So a couple cases where we do want to use client prediction is, anything that the player controls, we always want that to be client predicted. Because let's say, we didn't have client predicted and, we pressed say like the jump button to make a player jump. Well, we have to send that data up to the server saying, "Hey, I want to jump." And then the server basically, processes that data and says like, "Okay, yes, you can jump." And then it has to send that back to the client. And then, the client receives that and then, they actually jump. That takes quite a long time. So what we, end up doing with client prediction is as soon as we hit the jump button, we just run the jump logic, assuming that the server is going to say, yes, we can jump, because again, we're running that same code on the client. We have these same kind of constraints and parameters, and so the client should know if they can jump or not, right? So we want to just make the character jump as soon as possible, and then the server is kind of says hey, okay, this client is jumping. Let's run this simulation. If it were to jump. Now let's say that the client predicted that the player just kind of jumps straight up and lands back down in the same place. But the server says, okay, the client jumped, that's fine, but maybe someone actually like threw some like barrel or something, and it like hit the player in midair, and it kind of like knocked them over to the side a little bit. So then now the client kind of needs to like fix that behavior and then say like, oh, okay, I should actually be, over in this position. But so yeah, again, we just kind of want the player to immediately respond to input actions, even if it's not the thing that ultimately ends up sticking, but we still do want that, give that like immediate feedback to our players. So client prediction can also be used to predict the behavior of remote clients. So, based off of the previous data of remote clients, then we're going to continue simulating that data into the future. The idea behind this is that we want to be predicting, um, the network time that we're predicting should be like the same physical time that the server is simulating any given network tick. So this is kind of like a way to kind of try and mitigate some of these latency delays where we're, again, we kind of have some previous data from the server, but we're, predicting a little bit into the future about what these remote clients are going to be doing. And so, kind of along these lines, we have this thing called simulated rollback. Now, data is actually received from the server in a bit of a buffer. This has a couple purposes. One of them is to kind of avoid packet loss, where if there is some packet loss, then we kind of have the last couple data points, and that kind of allows us to kind of like run this simulation back with all the different data points. And so yeah, we can just kind of like re-simulate this data as needed. Um, there are some problems with simulated rollback. It can be fairly expensive because essentially what is happening is you're basically running like multiple you're simulating multiple frames of the game within one single frame, which can end up being expensive in some certain cases. So let's say your frame rate starts to dip down. Maybe some network ticks are missed, and we're kind of running this simulated rollback logic. And if we have to run this simulated rollback logic, and that ends up being expensive, that can cause our frame rate to drop even more. And then it kind of spirals out of control where this your frame rate can kind of like really just crash down. So that's why I say it's really important to, only predict the things that absolutely need to be predicted. So, maybe enemies that are close by, or other really important things. Whereas, enemies that are kind of further away, out of sight, whatever, maybe we can get away with having those set to interpolated, just so it doesn't take up these resources of simulating this rollback. I will say that this is quite important for dynamic physics objects. That's one thing that I've seen is resimulating the physics systems multiple times per frame can get extremely expensive. So we don't want to be predicting like a large amount of dynamic physics objects. I also will give a shout out to the Unity documentation, because they do showcase a bunch of really good examples and edge cases for client prediction and simulated rollback. So there's a lot of good things in there. Now, again, there are still going to be some differences between what the client predicts and what the server actually says happens. So, as a minimum, you might notice kind of some like jumping around. Say, for example, if one of the remote clients was running straight forward down a hallway, the client prediction would say, let's continue predicting that client to move straight forward. But then, the player makes like an abrupt turn to the left. Then, the client is still going to continue predicting that as going forward into the future, because there's no way that they can guess exactly when a remote client is going to change their direction of input. But once that's processed by the server, sent back to the client, then the client can correct that by essentially kind of re-simulating that behavior, and then now they're kind of like moving over to the left. So that's kind of like the minimum. You might see a little bit of jumping around, but unfortunately, it still can lead to some bad situations for maybe the client predicts that they did something good, but then the server says no, that didn't actually happen. Maybe for example, like the player kicked a ball into a goal, and then on their end they see the ball go into the goal, and like they thought they scored and everything, but then the server says, "Oh no, actually there was another player who came in and blocked that, and so that like actually didn't happen." Well, that can be quite frustrating because you see the ball go in the goal, but then a second later it's just like bounces off to the other side. So that's where things get frustrating and immersion breaking. But it's just really again the kind of unfortunate reality of doing client prediction, especially when there is some network latency involved there. So now I want to kind of dive into a little bit more of the tech that we get with Netcode for entities. Um, so one of them that I do want to talk about is worlds. Now, a world is a concept of Unity ECS. And a world is basically a complete simulation with entities, data components, and systems. And if we have multiple worlds running in one game instance, entities in different worlds cannot interact with each other. Now, in a typical single player game, just one default world is created. Um, and then say anytime that we create an entity, it's going to be associated with that default world. Anytime that we create a system, an instance is going to be created for that single world. And then that system is going to be running on, again, data components just in that specific world to make things happen in the game. Now, with Netcode for entities, multiple worlds are created. So one's going to be created for the server, and one is going to be created for each of the clients. Now, if you're running this in, say, dedicated server mode, this again is pretty similar to like a single player setup where just your dedicated server is just simulating the server world, and then each client is just simulating their own client world. Now, if you're running this in host mode, where one of the clients is also simulating the server, then they're going to be running both the server world and the client world. So they kind of have two instances of this game running. Um, Again, it's not like the exact same thing because some things are just running on the server, some things are just running on the client. But for the most part, when we're doing like predictive systems, a lot of that logic is going to be run on both the client and the server. And then so again, keep in mind that for every entity, component, and system that is kind of part of our game, one copy of that is going to be in this server world and one in the client world. So, there are kind of like two instances of every system running. For every entity, there's two instances of that on that computer. Um, so again, you're kind of just like running the game twice. I will say having these split worlds is really nice to have because we can easily just say, hey, run this system in the server world, run this system in the client world. We don't need to have like a bunch of split logic all over the place where we're saying, if server do this, if client do this. I mean, you still can have that, but it seems to just be a little bit cleaner when we're just kind of, specifying systems running in different worlds. So RPCs, they're kind of pretty common in multiplayer developments. Typically are used for kind of one-off updates between the client and the server. So, they're kind of like for, say, significant events like requesting to join a game or, telling all the clients to move to a new scene. They're not typically used for gameplay things. It's more kind of like the, higher level, things like, again, joining a game, changing scenes and all that. Um, so just to kind of show you about how these RPCs are actually structured in Unity ECS, it is a little bit interesting how we do that. In this case, I have an example RPC of, if a player wants to join a specific team, then we can create this data component. And you see this is called the MOBA team request. And it implements this IRPC command. So that's kind of to specify, this is like an RPC that we're going to be sending across the network. And so we can associate some data with this. So this is, say, hey, the data that we actually want. So this would be the team type. So maybe if the, player wanted to join the blue team, we could assign the blue team as some data in there that gets sent up to the server. So how is this actually done? Well, we actually create an entity, and that entity kind of sends that RPC request. So you see kind of in this middle image here, we're creating an entity. We're adding this MOBA team request data component to it. we're assigning the value of the current requested team. And then the way that we actually send this RPC is we add another component, which is the send RPC command request. And then we can set the target connection. So for the target connection, we actually need to specify the entity that we're sending it to. In this case, this pending network ID, it's going to be the server. So this would be like an example of, again, the client saying, hey, I want to join the blue team. Let's send this up to the server. And then on the server side, this is kind of how we interpret that data. So we can create a query which looks for any entities with a specific set of components. So in this case, we're looking for entities that have this MOBA team request, but also we're looking for ones that have the receive RPC command request. So when the RPC is sent, you can almost think of this like when it gets sent, this send RPC command request almost changes into a receive RPC command request. Again, it doesn't really change on the entity because it's going between a client world and a server world. But when this RPC entity is kind of created on the server side, it has this receive RPC command request. And so that has some information about, who sent this RPC. So we can actually, handle this request in a system and then, send back to, either just that specific client or all the other clients that, that connection went through. So again, these RPCs can go, from client to the server, from server to one specific client or all the specific clients. It's just kind of like a way to kind of broadcast messages between, again, client and server. Another interesting thing that is kind of available to us is command data. This is most often used to send player input up to the server, but it can be used for other things. It's actually set up as a ring buffer to kind of aid with resimulation and some packet loss issues. So you can actually kind of like go back in time. This would be especially important for input data, where if just on one frame, if a player presses a button and then that gets sent to the server, or they try to send it to the server, but there is kind of some network packet loss, and then the server never actually receives that hey, I pressed the jump button, then that's of course an issue. So we kind of want to buffer this data a little bit, so we kind of have like are actually sending like the last couple ticks of input, so we can see hey, if there was some packet loss, we can actually see if a couple frames ago that the player actually tried to send the jump button. So we kind of have that. Here's kind of a little bit about how this command data looks. So the one on this top, I'm kind of like setting some cooldown target ticks. So I'm kind of using some network ticks to say, this is when a particular ability should go off cooldown. Typically, we want to use network ticks for timers like this, just because it's a little bit easier to kind of like synchronize that data across the network. So you can see that this is set up as an iCommand data. With this iCommand data interface, one thing you do have to implement is this first line here, which is the public network tick called tick, which has a getter and setter. And then, so anytime we're kind of like assigning data to this, we kind of need to like set the, the tick number that we're setting this data for. So we can say, hey, on this particular tick, we're setting the rest of the data components. In this case, it's the AOE ability and skill shot ability. And then so the server, when it receives that, it can look at a particular tick to see what that data was. And again, by default, this is kind of stored in a ring buffer, which I believe is 64 elements by default. And one thing that Unity kind of did is, because again, this command data is typically used for input data. It's like having a nice stream of input data. They also created this input component data, and this one acts a little bit more like a regular data component where we can just kind of set the data value on it. And it's kind of like a wrapper for this command data, um, where it actually kind of implicitly sets this tick value, um, so that we don't have to worry about that for for input data, which is nice. But again, we still do have the ability to do some things a little bit more manually with the command data there. So another great feature with Netcode for entities are ghosts, and ghosts are basically entities that are replicating data from the server. And so ghosts can either be predicted or interpolated. Again, we kind of talked a little bit about interpolation versus prediction. And so you can see when we're kind of doing our authoring, which was we're setting kind of like our initial values, we can set a default ghost mode. So this can be interpolated, predicted, or owner predicted. And again, we can kind of change these on the fly. So maybe something by default is set to be predicted, but then once they're actually in the game, we can kind of determine hey, this thing is, actually a little bit further away than we wanted. So, maybe we'll make this an interpreted one. You can see there's also some other things that we can set on here, such as importance. So this is kind of gives the simulation a little bit of a hint about how important something is. Something with a greater importance value is more likely to send more frequent updates. So, maybe we can have something that is set to predicted, but maybe it's not as gameplay critical as like some other players in the game. So we can set it to be like a lower importance value. So, it's still receiving updates from the server, but maybe not as frequently. That's just kind of like a way for, the network traffic to be kind of metered. So we're not like, sending too much at one time. Um, and there are also a whole bunch of, other additional options that we can set. We can get real granular about, how data is being synchronized. But anyways, the whole idea with ghosts is that again, the server is kind of simulating these ghosts, and then that data gets sent down to the clients, and then whatever data that we're kind of specifying as ghost data is just going to get overwritten by what's ever received from the server. So how does this practically work? So we have these things called ghost components, and you can see that in this case, we have this like ghost component attribute that's going over this damage buffer element. Um, and we can kind of specify some options on here. So this is set to a prefab type of ghost prefab type dot all predicted. Now, what this means is this means that this component is only going to be on entities that are considered predicted entities. Um, this is kind of like a performance optimization because maybe in this case there are some um, particular systems and components that we only really want to run on things that we're doing predicted data for. So this, the way that I've kind of set up this little combat system is that we have these like damage buffer elements, and if something gets damaged in a particular frame, then we kind of add to this damage buffer, and then like kind of towards the end of the frame, we accumulate all this damage in this damage buffer, and then use that to set the current health of an entity. Um, and this is something that we really only care about predicted entities for, because we want, if we're predicting an entity, we want its damage, to be updated immediately on the client side. Whereas if we're interpolating something, then all we really care about is updates to the current health that we're receiving from the server. So we don't necessarily need to worry about predicting its health in the same exact nature. So what this again attribute does is this will add this component to any entity that is predicted. I mean, not any entity, but like any entity that we specify. But if it turns to an interpolated entity, then this component actually gets removed. And then the way that Unity ECS works is if an entity doesn't have a component, then it doesn't participate in those systems. So again, it's a little bit of a performance optimization because it's just not participating in those systems, which is kind of nice. And then you'll see the other kind of attribute that we can have in this lower image here is the ghost field attribute. And this essentially means that anything that is stored in this field is being kind of like received by the server. So if you have this ghost field, you can't really set any data on it, like on the client side, because once the server receives, that data, it's just going to overwrite that data. So yeah, again, these ghosts are really just kind of like replicating what they're receiving from the server. So to talk a little bit about the different systems that we have. So this would be like, how we can specify where we want systems to run. So in this case, we have say like a movement system, this champ move system, and we want this to be a predicted system because of course, if we have a player, we want our player to immediately move as soon as we press any move input. And also for any remote clients, we want them to be moving right away as soon as we get any movement from them, and we do want to continue to predict their movement as well. So the way that we specify to make a predicted system is we just tell it to update in the group, which is this type of predicted simulation system group. Now, if we don't like specify if we want this to run on the client or the server or what have you, by default, it's just going to run on all worlds that we created. So, client worlds, server worlds, anything else like that. And so again, these predicted systems, we want these to run on both the client and the server. So they're running the exact same logic. So then, the two images below is how we specify if we want a system to run in the client world or in the server world. So you can see the health bar system, because this is, it's just something like UI related system. We only want this to run on the client. So we just kind of add this attribute above the system where we say world system filter, and then we can pass in the world system filter flags that we want. In this case, it's going to be the client simulation. So this is only going to run on client builds, or in client worlds rather. And then for say something that we only want to run on this server, like the server process game entry request system. So it's kind of processing the says like, hey, like a client says, hey, I want to enter the game world. The server should kind of process that and allow them to enter the world. Well, this is a server only system. The client doesn't need to run this at all. So we can do the same thing, but we also have a world system filter flags for the server simulation. Another cool thing that we can do with Netcode for entities is have thin clients. Now, thin clients is just kind of a way to test network traffic and behavior, where we are kind of like create simulated clients to run around in the game world. Typically, in most cases, you're just going to want to have these like join into the game world and enter random inputs and just kind of have them move around to test network traffic. Of course, if you want, you can get more complex and like actually have some like maybe AI behavior that's kind of controlling these to, act as if they were a real person and kind of like making certain decisions. But really, it's just like a great way to test what your like how your network traffic is going to react with like like a full lobby of players, because say you make some major changes to your game, and you want to see what the network traffic is going to be like, how things are going to react. You don't want to have to like gather up a group of 10 people every single time that you do that to test it all out. So on your computer, you can kind of simulate these thin clients to kind of get an idea about how the different client predicted systems are going to work and all that. So I think they're a really great feature to have and test with. So when you're creating builds of your game, you have a whole bunch of options. You can create dedicated server builds, dedicated client builds. You can create host builds, which have both the server and client on them. If you want your server build to be a headless Linux build, you can do that. And then your clients, they can be whatever platform they want. There's just a whole lot of options for them. Um, and so, yeah, you can use, Unity has some services available that allow for hosting the game, peer-to-peer relay, matchmaking. But you're not locked into using Unity services. You can use any services and host it on AWS or Azure, and create your own server network infrastructure. You really have a whole lot of options. So you're not locked into using one thing or another. So I do want to talk about some of the tools that are available with Netcode for entities because I think there's some really cool tools available. One of them is multiplayer play mode, where you can essentially run multiple instances of the game on the same PC. So you really can just say like, "Hey, I want to run the game with 4 instances of the game," and so you can easily just configure that, hit the play button, and then all the windows pop open, and you can click into each window, control each one, and so you can see how the game is going to react when you have um, multiple yeah, remote clients and everything like that. So you can test out what client prediction is going to look like, and if there are any issues for running on like remote clients versus like a hosted mode. Um, so yeah, and you can get individual log messages for each of the connected clients. So it's just real nice for debugging. Like if you're running into something where like only on connected clients you're seeing some issue, you can kind of have some debug log statements in there to start to look into what the issue is. Some other tools available are the play modes tools window. This one's really cool because you can kind of specify if you're running the game in client mode, server mode, client and server mode, and it gives you, here's where you set how many thin clients should be spawned into the game, and that's a whole lot of options for testing different network latencies and just kind of like network issues you might experience. You can kind of like set all these, have some lag spikes, and just kind of be able to test your game and see how it reacts to all these different network scenarios which you're going to experience in the real world. So I do want to talk about a couple of different learning resources. Some things that I've kind of created here. So if you're completely new to ECS, I would recommend checking out my survivors like tutorial, where I created this with created this simple little survivors like game using dots and ECS. I think it's a good introduction to ECS, kind of like go over some of the theory, as well as just kind of showing you how to set up a simple little game. Um, and so, yeah, definitely check that out if you're brand new to ECS and just kind of want to figure out how to create a simple little project. After that, if you want to do any netcode for entities specific things, I did create another full tutorial about how to create a multiplayer game with dots and ECS. By the way, both these videos are available just on my YouTube channel, Turbo Makes Games. And so this one, it kind of assumes that you have a little bit of ECS knowledge, but I go into how to set up like all the netcode for entities specific things like handling input, doing client prediction, running things server, client, all that. So definitely a fun video and recommend checking that out. And if you do want to get a little bit more into some of the intermediate ECS things, I did mention that earlier this year I published this game Dot Survivors, which is available for free. You can download it, play it around if you want, and it performs great. I think it's a real great showcase of creating a game with dots and ECS. running in the game on a Steam Deck, it's locked 60 frames per second the whole time, even with a lot of enemies on the screen. So I'm really happy with the performance that I was able to get out of it. And then also over on the Unity Asset Store, I have for sale basically all the project files from the full shipped Steam game that you can purchase through there. And then I have this like big documentation site set up where it shows all the things about creating a full game with Dotson ECS. So if you want to learn a little bit past like just a simple little tutorial, and you want to see all the considerations you need to make for a full Steam game, I would recommend checking that out over on the Unity Asset Store. So anyways, that's my talk on an introduction to Netcode for Entities. I hope you enjoyed it, and I think we're going to get into some questions and answers now.
Yeah, fantastic session. Thank you. There's a lot going on in that netcode stuff, isn't there?
Oh, absolutely.
Yeah, it's yeah, my head's buzzing a bit with all the differences between interpolation, the prediction, and so on.
Yeah.
I'm going to jump in with it's a question for me actually.
Okay.
The ghost components, I didn't quite get what they were for. Would you be able to sort of give an example, perhaps?
Yeah. So that would be for basically if you had say like a health component on like a remote client, then and the server kind of says, okay, the health actually like decreased at this time, then that data gets sent down to the clients, and then whatever data is received from that is kind of overwritten on what it had on its like local copy of it. So that's just kind of like the fields of it. But then the ghost components would be for if something is interpolated versus predicted, you could have that component on an entity or remove it depending on just kind of the performance optimizations that you want to do.
So it's basically just to say I'm going to work on this, locally because I'm going to try and figure out what it is, but actually it's not an authoritative thing. Someone's going to tell me what the actual values are.
Right. Yeah.
With you. Got it. Yeah. Alex, do you have any questions?
Sure. Mine, I am kind of far away from Unity and whole stuff. I will always like, when I hear about the dots and CI system in Unity, I know that it's been around for so long time, but do you know what the adoption rate? Like, does it, studios usually use it for the production?
So yeah, as far as like percentages, like I obviously I have no idea, but I do know there are some like big name studios that have been creating games with dots and ECS. Unity has kind of promoted some of them. But actually, if you go on SteamDB, which is a great website to get a lot of information about Steam games, if you go to like a game page, there's like a metadata section, and so you can see if a game like has the entities package installed. I mean, obviously, it doesn't tell you if the whole game is made off of entities, but it can show you if that package was installed. And so you can actually search by, like, you can filter by all the games that have that package installed. And I think there's like over 500 Steam games now that have it on there. So it's I mean, it's been used for a fair number of projects.
Mm-hmm. So you'd say it's fairly stable these days. Not perhaps no longer experimental.
Yeah, and that's one of the things that I wanted to really test out with my Dot Survivors game is like, could I make a full, shipped Steam game, and what's that experience like?
Mm-hmm. That does look like a great set of resources actually for understanding how this thing can work in action.
Yeah, I'm
That's
really
true.
happy with it.
I mean, 500 games is like an hour of Steam. Like every hour, 500 games are being released.
True.
Matt, do you have a question?
Yeah. I was going to ask. I think you perhaps kind of covered it a little bit with was it Island Kids or
Survival Kids.
Survival Kids. There it is. Because as I understand it, dots, ECS, and game objects can be used in the same scene quite happily. So what happens with game objects that need to have some kind of network stuff?
Yeah, yeah, that's a good question because yeah, and even with the Dot Survivors game that I created, there was a whole bunch of things that I still had to do with regular game objects because ECS doesn't have like an ECS version of everything.
Hmm.
Typically, like UI, audio sources. These are kind of like some of the more notable things that don't have their ECS equivalent yet. So we kind of have to like create a little bit of a bridge between the ECS side and the game object side to kind of like trigger things to happen on the game object side and kind of vice versa. And then yeah, as far as like any network synchronization goes, um, again, all the entity stuff is what's being synchronized. So as long as you have some like systems that are kind of like interpreting those changes on the ECS side to trigger things that happen locally on the game object side, then that's kind of how you would approach that.
Okay. Yeah, that doesn't sound too painful at all, really. It's just a bit of wiring up.
Exactly. Yeah. Yeah.
Hmm. Hmm. Cool, cool. Did we just get a message in the chat there?
Yeah, actually. So the question is about the input latency. So you can easily simulate the instant inputs on the client side, but what about like a remote client that is, I don't know, like doing like a thin client doing actions, and it takes forever for the like a thick client to process it.
Yeah, yeah. I mean, again, there's always going to be some type of network latency. And actually, a fun little exercise that you can do, which is like kind of a good way, I think, to start wrapping your head around, how client prediction works and everything in Unity ECS, is to just like create a simple little scene where you kind of have, just like some little objects that, kind of move around and like react to your input, just kind of like going side to side type thing. And if you add in some network latency with these tools, you'll see that for your local client, as soon as you press the movement button, it'll start immediately going. But then if you have like a separate window where it's kind of like your local client is that remote client, and you kind of have that latency in there, you'll see that the player that's kind of representing the one that you're moving will just stay still until that network catches up, and then it'll like jump ahead to like not where it was received but where it's like predicting to be now. So it should effectively be in line with what your client is. But then you'll also see that as soon as you stop moving, that client is going to continue on for a second, but then snap back to where it should stop.
Yeah,
Got
I
it.
think the sorry, Alex, go
No,
go.
no, no. I hope we've answered the question.
Yeah, I think so. I think the tools are really useful there as well. Actually, that panel with the being able to simulate latency and stuff looks like it's going to be really useful. And as you say, can be a good way to get your head around what's going on.
Yeah, yeah,
Um,
I found
I,
it
I'm
very helpful.
Yeah, I'm going to give a shout out to Ryder as well because I know that Ryder supports listing the different editors in the debug window, so you can actually choose which one you want to debug. So just have to
Yeah, yeah,
do a small shout out.
yeah.
Speaking
I
of
think we
Rider, I
should.
know the tools that support CCS system out of the bat.
Hey. Right, I think we've just about run out of time there. So thank you again, Johnny, for a great session, and lots of great resources there. I think in your talk as well. So thank you very much, and we'll see you soon.
Sounds great. Yeah, thanks again for having me. And yeah, enjoy the rest of the conference.